You are going to have a Google question of the day. It'll go live, I don't know, about 10, 15 minutes or so. So here's what we're doing today. We're going to just talk about conversions. I started this topic yesterday, and now we're going to really kind of go in depth into it. So it's to know the differences between radians and degrees. That's kind of the big thing today. Once we learn that conversion, you guys know what? The Google question will seem super easy. There's 2 parts of the Google question. I'll explain it when you get there. Now, after we're done with that, then we're going to just talk about a new topic, which is why do we even have radians? There is a reason, and there's a whole set of mathematics based on it. So that's what we're going to look at today. We're going to intro it for the first time, and that's what kind of our assignment is tomorrow. This is I think the most interesting stuff about angles is the stuff we're going to look at today to start with. I really like this stuff. So, but yeah, so let's kind of work through it. Now, again, what we talked about yesterday was degrees. This is a degree. We have different classifications: acute, right, obtuse, acute, right, obtuse, straight, and reflex. These are my angles. We have other types that we're going to look at today. That's a part of the conversion stuff we're going to look at. But what we talked about yesterday is how you actually estimate these and how you use these objects to measure. This is something we're going to do probably later this week. I think I said maybe Thursday this week. We're going to look at measuring. So you're going to get one of these in hand to measure angles. I know that seems tedious. It just helps. We did it a little bit in geometry, if you can remember back to those days. So we're going to look at those again. Now, we need to talk about some new types of angles, and that's something we didn't do yesterday. I want to talk about standard position for drawing angles, right? So, all right, so standard position. There we go. Standard position for drawing angles. This is something that a lot of people just never get to see. They don't understand it. This explains where the symbols for some of our mathematics comes from. Standard position is when you have an angle and you draw it on a coordinate plane, a graph. So, in fact, I'm going to share a graph with myself just so we can use that to draw. Where's my in-class notes? There we go. Let's share this so I can use this to draw on it. All right. Okay, it's going to pop up, sorry. All right, so we're going to use this graph here in a second. Let me go back and add this in. All right. Okay. Whoa. Too big. Calm it down. All right. All right, so when drawing an angle, what you're supposed to do is, I'll try to put this in a pretty bright color. Let me know if you can't see it. But when you draw an angle, you start on the origin, and you always draw the first line going to the right along the x-axis. That's what they call the initial side. Okay, so the initial side is that first wall. Initial side or initial ray. It always goes along the x-axis to the right. Then what you do is you open up counterclockwise. You open up counterclockwise, and wherever you stop, that's how you measure your angle. So if I stop up here, and I stop here, there's my angle. Okay, now, they have Greek letters that they can use in your textbook. You'll see that. We did a little bit of that in geometry days. The Greek letters, when they label angles, we have theta, beta with a really long tail. We have phi or phi, however you want to say it. And then we have alpha and gamma. We have certain Greek letters. They use these for angles. So you will see that a lot throughout this chapter. They'll just randomly throw these angle-like symbols in there. They use Greek letters for the angles in the corners. The reason why is that they use capital letters in the vertices for naming like an object. They put these symbols where angles sit, and then they use lowercase alphabetical letters for the wall lengths. So they're very distinct when you look at a drawing. Am I looking at an angle, or am I looking at a wall, or what am I looking at? You should know. An angle, they use Greek letters from now on. All right, questions with that? Now, if you're going to measure it, you put your protractor down, you line up your one wall, and then you actually measure it going up. You guys know the drill for that. But this is how you draw in standard position. Every single time you draw it to the right, you open up clockwise. So that's standard position. So it doesn't matter. It doesn't matter if you don't have the graph. Like a lot of you don't have graph paper. I understand that. So you just, when you draw, you go to the right, you open up, counterclockwise, and wherever you stop, there's your angle. You don't have to have a graph. You just have to make sure you start the same way, going to the right, open up. Now that's how you draw a positive angle. So let's say this is like 110 degrees. Bless you. Now if you open up the other direction, that's a negative angle, like when you open up towards the ground. So if I open up this direction, so if I open up this way clockwise and I draw my angle, that's a negative angle. Let's say that's like a negative 70-degree angle. That's an angle of descent. It's like when you're in an airplane, you're looking down. It's called an angle of depression. You're looking down at the ground. It's a negative angle. So you know like what angle you need to tilt, the aircraft to look down towards the runway, that type of thing. Okay, questions with your degrees and angles. Now today, what we're doing in the Google question of the day, we're going to take these angles and convert them to radians. So if you don't remember what radians are, it's a different form of measurement. I compare it to like if you're going to use a ruler to measure in inches or feet versus the metric system, centimeters, meters. Like it's just a different label. I know there's a difference in length, but once you know how to convert them, it makes sense. Like it's a different way of measurement. They still can be representing the same thing, and that's what we're going to look at today, like those conversions. I didn't really talk about those yesterday. All right. Questions with that? Okay, let's jump right in. Let's talk about radians and we'll talk about conversions. Radians, if you don't remember, this is what I showed you yesterday. 1 radian is when you travel along a circular path and the radius is exactly the same length as the actual like arc length that you traveled. So if you look up here, my radius of my circle was 12 millimeters, and I traveled along the circular path 12 millimeters, that's 1 radian in terms of angle. Then if I went another 12 millimeters, that's 2 radians. If I went another 12 millimeters along the circular path, that's 3 radians. And what we talked about yesterday was like a radian roughly is about 57 degrees. That's roughly what 1 radian converts to. So then when you actually do it, so like when you actually convert, you can figure out that the angles are really large. So 3 radians converted out to be about 171. I think we did that problem in class yesterday, correct? That was the one we did. Question?
Okay, this may be a really stupid question.
Nope.
Probably. Okay, so do we actually take 3 times 180, or does like 1 radian equal like 12 millimeters?
No. You actually take 3 times 180.
Because 1 radian was like the 12.
Yeah. What I'm showing you up here is how do they come up with the label 1 radian? It doesn't have to do with 12 millimeters, right? It's not that number. I just made up numbers just to show you how do they like draw 1 radian in terms of angles. Okay.
Well, I said it might be.
No. That was good. That was a good question. So hey, if you didn't understand what she was asking, the radian angle itself has nothing to do with the 12s here, because I'm just showing you how did they come up with like what is the standard of 1 radian? Like why is that a thing? It's because the radius of your circle equaled the distance you traveled along the path on the circle. That was 1 angle radian. Okay, that's how they defined it. So it was a really good question, because like when I convert it, I don't use the 12 at all. I'm just saying, okay, 3 radians, this is the angle that it is. Take it times 180 divided by pi.
So it's always going to be the same?
Yeah, so whatever, you're always going to use that 180 over pi because it always converts the same way. So that's how we convert it to degrees, or we go backwards.
How does that always work out, though? Because shouldn't it change?
Well, it's not always going to be at 171. That 180 over pi is the default conversion for how you convert from radians to degrees or vice versa and go back, because they defined a circle, in what is that, the first century, right? The Greeks figured out pi is related to like the path along a circle, so that's how they converted angles. They've realized that there's a direct relationship between that angle you're taking and this radian measure.
But each radian could be a different length.
No, so it didn't matter, so this is a good question. So, right, it doesn't matter if I pick 12 millimeters, so it doesn't matter if I pick 12 millimeters or if I go 20 yards, right? It didn't matter if I did that. When I travel that path, right, and I go that same distance, this is still the same picture. It doesn't matter if I made the wall shorter, it's still the same angle. So it didn't matter if, I went 2 yards versus 12 millimeters, 1 radian is still that same measurement. It didn't matter the length. What I'm trying to explain to you, so I'm not confusing you, the lengths of these walls don't make the angle. The space here does. So it doesn't matter if I use 12 versus 24 or anything like that. Does that kind of make sense, or am I off on what you wanted?
Sure.
You're finding the answer.
You're not convincing me at all. I think I just confused you even more. I'll come back to it. Okay.
So like 3 radians are always going to equal that.
171. Yeah.
So I can't have done that exactly.
I just don't, okay, having that long wall and that long wall, I don't understand, because like, if your bottom one is like 12,
Yes.
that would make your outside one 12.
Yes.
It's just time to wake
So
up.
wouldn't that make your ankle bigger?
No.
Come on.
Because the actual wall lengths themselves don't matter for the angle itself. The reason why is that
Because they're the same.
in terms of like angle here, it is the same angle, right? Because no matter how long your walls are, that doesn't change the angle where it sits. It's called a central angle, right? It's in the middle of your circle. It doesn't make a difference in terms of like pie crust or the length of your radius. As long as you're traveling the same distance in terms of numbers, it will always make the same angle.
No, I'm serious, I actually
It's
do.
like saying like if you have a square
Yes,
that
I get it, I get
walls
it.
like 5 meters
Apparently you
or
don't.
8 meters.
I think she actually does. So, stop. You're confusing me. All right. So,
You just gotta wake up.
now, all right. Now, okay. All right. So,
Distance is irrelevant.
I'm not gonna talk about that.
now, hey.
Is there a question?
So let's talk about conversions here. So this will be a part of the actual part of your Google question of the day today. So I'll give you an option for making angles. So pick any angle in the 200s.
400
Say it again.
247.
Okay, 243 or 247. Ooh, what am I doing? Sorry. All right, so let's go with 247 first. Then we'll do something with 400 and something. So okay, so do we agree this is in? Do we see that this is in degrees right now?
Yes.
Okay, so this is in degrees, and what I want to do is convert this. I want to convert this into radians. To know what that is in terms of radians, like what that number would be. Now, I can ballpark it in my head without using my calculator yet. Okay, so what I mean by that is 247. If I look at a drawing of that, right? A drawing of 247 on, like standard position. So 247, I'd start here, I spin around counterclockwise, and it ends up like over here somewhere. Right, that's my angle. That's a 247 or 43 degree angle, right? Because how I know that? Going straight across would be a 180, and I went past 180. And going straight down, so if I went all the way to... So all the way to here is 180. If I went to here, that's 270. Right? Because those are your major, what they call quadrantal angles, the ones that land on major quadrant lines, the axes. So... I didn't go to quite to 270. I landed on 247. To convert that into radians, I'm going to think about that drawing I did earlier. 1 radian is going the same distance along a circular path that your radius is. Now, I didn't draw this nearly big enough. So whatever this radius is, if I travel the same radius here, that's 1 radian. And so if I do it again, this would be the second radian. This would be 2 radians. 3 radians is over here. 4 radians. And so I'm ballparking that I'm around the 4 or 5 radian mark. Okay, somewhere in that ballpark. 4 or 5, somewhere in that general range. Okay, does that make sense in terms of just like guessing where that thing is going to be?
Here.
Again, how I know that, as I'm looking at what my radius of my circle is, traveling along the same path, that's 1 radian. 2 radians, 3 radians, and I can just kind of ballpark where I'm going to land. Instead of ballparking and knowing kind of in my head what it's supposed to look like, we have that conversion tool. Now this is different than yesterday's, right? I'm starting with degrees and I'm going towards radians now. So to do that, you flip the fraction over. So to go 2 radians, here's what we have, and I'm going to explain why this works. You multiply by pi. I don't know why I just wrote r. You multiply by pi, and you divide by 180, and that will give you your radians in terms of number. It'll be a decimal usually. You can leave it a fraction. I actually prefer if you leave it a fraction instead of like give me like a crazy decimal across your screen. I'll explain it here in a second. Okay, question.
Why can't 1 radian just be like 90 degrees?
I know. The reason why they picked that radius and that is because of this idea of converting using like pi and 180. The way that I showed you how a radian is set up wasn't the original way that somebody created it, right? It was radians were created when they looked at circumference of a circle versus like the angle, and that's where it was actually came from. What I showed you yesterday, that idea of like drawing a radius and drawing the same path, that was just a coincidence in what always happens. So it was, I'm like showing you the end result and kind of going backwards. So yeah, I agree. Like, why did they pick 360 for a circle, right? That's a weird number, right? It's just like why do we pick 5,280 feet for a mile, right? That's a weird conversion. It's because of just the way that we established what 1 foot was, and it's a coincidence that it's 57 and not like 90, let's say, right? Yeah, it's just this weird path that we've kind of traveled down. Why a circle is 360 is because of the orbit around the Earth. They thought it was 360 days. That's why they've established that, because they thought we were in a perfect circle around the Earth, or around the Sun, I mean. So that's a little bit of history and math. Question?
Can't you just do 247 divided by 180 over 5?
Say it again?
Can't you just do 247 divided by 180 over 5?
Yes, that's what we're going to do. That's what we're going to talk about. Yes. So if you didn't hear Bree, she's already multiplied the fraction and kind of wrote down what her answer is. The exact answer is like what she said. You take the 247, you divide by 180, and you multiply by pi. When you multiply by the fraction, you just multiply to the top, right? Because this is technically over 1 and you go. And this technically is the exact answer. Now, if you can simplify that fraction, simplify. Now, if you don't realize this, I don't know if I have any. Oh, here they are. My calculators can simplify fractions for you.
No way.
They can simplify. They have a little ABC button. So over there, if you want to grab that little sticky note again, move that sticky note diagonal up where it says the ABC button, right there. Right where that little arrow's facing, there's an ABC button on my calculator. That's how you establish fractions. Now, what I'm going to do is not type in pi. Okay, so now it might actually convert this to like a mixed number because I have a bigger number on the top. But I'm going to show you how this works here. All right, so to type this in, hopefully you guys can see that. Oh yeah, you can see it. So I'm going to type in my 247, and then I'm going to hit the little ABC button, so it puts a little fraction bar. That's a little like back arrow. This again, I use this little ABC button. Then I type in the 180 because that was the bottom number. Then hit enter, and it converts it to like a mixed number. It's 1 and 67 eightieths. Or if you want to convert that back, you can hit the little ABC button again, and it will convert it back. So I'm going to hit second and convert that. So it goes to like an improper fraction. So I hit second and that, and it will actually convert it, and it goes right back. It didn't actually simplify. There's nothing to simplify here. So like for instance, if my fraction was like, let's say it was 8 over 180. So maybe it was like 8 degrees, and I want to convert that to radians. 8 divided by 180, and I hit enter, so I use that little ABC button. It'll actually simplify the fraction for me. It's 2 over 45. And I'd put a pi on it, right? Because pi, you don't even need to put it. So that's if you have like weird numbers. Mine didn't actually even do anything, right? That my fraction didn't even simplify, so I leave it 247 pi over 180. Now, the decimal of it is you just type it in your calculator exactly how you see it, like what Bree was saying. Take 247, take it times pi. We have a pi button on your calculator. So 247 times pi, divide by 180, and the decimal I'm getting is 4.3. And there's a ton of decimals. It's 4.3 radians. So my number was close. I didn't quite get to 5 radians. Again, I'm ballparking. I'm just like guessing what these numbers are. Okay, did everyone see how I did that?
Oh, you're.
I actually prefer the fraction, just leave it. But I also can see the purpose of having like decimals as well. It's nice to see that I'm going like 4 perfect radians.
Why wouldn't we want to get to that answer?
Why wouldn't we go to the decimal?
Yeah.
Sometimes it's easier just to leave it a fraction because the numbers will work out nice and pretty. You'll see that why we have this. Like, why do they even create radians? Like, you'll see it today. We're going to show you that. And it'll make sense, like, why they leave it a fraction sometimes. So, yeah, we'll come back to that. It's a good question. We'll come back. All right, questions with the conversion, how to make things into radians?
No.
So, again, why radians is a thing currently, why we use it is because of this idea, like, going 4 radians. I was nearly all the way around a circle at 4 radians. I was like halfway around. So about 7 or 8 radians would get me all the way around. That's a smaller number to deal with than saying, 360 degrees. That's too big of a number to work with. So I can actually get smaller digits. Smaller numbers are easier to do in my head and to do on calculators. Because, again, the reason why they did this is because calculators back in the day, not these, had a limit to 8 numbers on your screen. Having 4.3 is an easier number to type in, as opposed to 360 or 247 or weird numbers. Okay? All right, now again, this was going from degrees to radians. You're going to have to do one of those today in your homework. Does that make sense, or do we need to do another one?
Oh, we're good.
Good. All right, you're going to have to do one. You take it times pi, 180. Now, I did not explain why is it pi over 180. This is something that you need to realize. It is a conversion. This is radians. These are degrees. And when you multiply by the fraction up here, the degree symbols cancel out because of labeling situations. What do they call that in chemistry where labels cancel out? What is that called?
Mold?
No. I know what you're talking about.
That's the only kind of.
No, it's what is that where you, there's a,
Stoic?
nah, not stoic, no.
It's stoic geometry.
Stoic! I'm pretty sure it's stoic.
That's stoic geometry.
Is that what it is?
Stoic!
Yeah.
No, it's
It's
that's
just,
like stoic geometry is using it. It's
it's where you change labels.
yeah, just give me a second.
There's a word and I know it too. I'll talk to Albertson or your father later.
Evan's
They'll know
not
it.
smart. He can't
All right, probably stoic, probably. All right, let's move on. All right, we'll come back to it if you think about it. All right, now, if I were to give you radians now, so let's say I were to give you, let's say I were to give you a radian, and I want to go 2 degrees now. So this is what we did the other day. So if I were to give you a radian, so some weird fraction, let's say I have like 8 pi over 3 radians. Now again, when they have a pi in the problem, it's probably a radian. They don't have a degree symbol, we assume it's radian. If they just told me it's 4, I assume it's a radian, unless they put a degree on it. Then it's in degrees. Right? So that's a weird thing that you need to get used to. So 8 pi over 3. I'm going to convert this to degrees. So how you do this? You multiply by 180 over pi. Now, how do I know that that's what I do and not the other way around? Because here's what I want. I want the radians left on the, I want the degrees on the top and I want the radians on the bottom. So like when you do labeling in chemistry, these cancel out, the radians are gone, and I'm left with just the degree symbol. Does that make sense in terms of labeling? Why? That's how I can tell which fraction to use. Is it pi on the bottom or is it on the top? Well, what do I need to cancel out? If I need to cancel out degrees, put the 180 on the bottom. If I need to cancel out radians, put the pi on the bottom. And so what we're going to do is we're going to take 8 times 180, and then divide by 3 because the pi symbol's canceled out. So 8 times 180. 8 times 180 divided by 3. What are we getting? I got 480. So 8 times 180 divided by 3. The pi symbol's canceled out, so I don't need pi's. Did everyone get that? No? Yes? All right. Your Google question of the day today is exactly this. I'm going to give you about 5 minutes here to go try out. There's 2 problems in the Google question. Convert one angle into radians, convert the other one into degrees. So,
I didn't get that from that.
Board? Is it?
Paige is just dumb. It's fine. I tried it.
Is it possible to get
no
one
idea what I'm
360
doing now.
degrees?
yes.
Converting?
Yes. Yeah, like this one. Mine was over 360. It was 480.
So, 300.
So yeah, so whatever angle I give you, if it's in radians, you take it times 180 over pi. And the pi's will cancel out and you go from there. If I give you degrees, you have to multiply by pi over 180. Is that, hey, dimensional analysis?
Yes.
Yeah.
I've been trying to look it up.
Good call.
Guys,
I knew there was a term for changing later.
Use dimensional analysis for study.
Yeah.
350.
Yeah.
Yeah, I knew there was a word.
What?
What'd you get?
For what?
The question.
401.
No.
5.34. Numbers. For which one? There's 2 questions.
Okay, y'all calm down.
5.34.
Y'all need
I
to
got 5 points. You make them pies.
I also got
pipe down.
Maybe I got.
Okay.
Just say pi, pi. Hey, if you ever have to write pi, just write pi for pi. It's up there. Just write pi. Pi. Because I know one of them you have to write in radians.
7 times 180.
Divided by 4.
That's not even the same song.
Yes, I'm aware. I always sing it like that,
Because
bro.
4's the other number.
Where's the pi sign? Oh,
Do you not see where it says 7 pi divided by
It's like
4?
with mine, I did 8 pi over 3.
I'm gonna actually
You have a
freak
big
out.
problem there, buddy.
Ward,
Oh, yeah.
do you not see your
Definitely
question?
gonna retake that.
It's just a fraction.
Ward?
I did 8 pi over 3. That was my random example I made. Question.
Not move on to this topic for a couple
5.23.
days.
We're not. We still have a lot to cover.
A very good.
Can you tell me if I'm right?
For what?
I did not
My
understand.
answer?
Oh, I see.
Wait,
What did you get for the?
Oh, wait, hold on.
Kelly, you can see classmates' answers.
You can leave it a friend. You get 5.
What did you get for the
Can I
second?
change my answer?
Yeah, it won't let me change my answer.
What did you get for the second?
Mr. Ward? Mr. Ward?
Sorry, so 300 times 180 divided by pi.
I'm also really gone, so.
Oh wait, no, I lied. I didn't do that. I did 300 times pi divided by 180.
Yes.
And that's what I got.
Yes.
And then for this one, I did 7 times 180 divided by 4.
Do y'all get 315?
Did you get 350?
I did.
Joey.
Don't go off for my answer though.
Whoa.
No, I feel like
I have to fix that something. Wait, what did you get for number 2? I'm working on it. So I messed it up.
What?
So it's
0.0129.
I got 315.
Okay, I got
By
315.
that.
Diana just do it
Is
by
it divided by
herself.
Oh, I didn't divide it.
What?
It's
Diana just do it
315.
by herself.
You're 315.
Okay, I got 315. What'd I do wrong?
Okay,
No, you're good. Is that the second one?
Yeah.
Yeah, that's right.
Did you guys see that?
What?
Oh, yeah, on his story.
I don't know
Kato
what the
put
extra is.
Trying 315 for specs
Be able to.
He can't. I don't think he can sweat his own weight. No, he can't because he's 350 pounds.
You just need to be bigger.
I'm getting there.